Okay, so we're going to go over 12.4 plate boundaries and hotspots. And as we go over this, you should have your reference table open to page 5, which is going to look like that. And one of the things I want you to notice before we get too far into this is down here at the bottom of page 5, and we have it listed right here. These are the keys that we're going to be using to identify the different types of plate boundaries. Okay, so there are 3 main types of plate boundaries that you need to know. The first one is called a divergent plate boundary. That means that the plates are moving apart from one another. This type of plate boundary is shown with this sort of like, I don't know, it's kind of like a step ladder. And you can see that the arrows on either side are pointing to show you that the plates are moving away from one another. Now, this type of plate boundary is caused by convection in the mantle, as all types of plate tectonics are caused by plate or by convection in the mantle. And in this type, the convection cells are going to come up and then move apart. All right, so at the surface, they're moving apart, and that creates this divergence that we see. Here's another look at it. We can see that magma in the asthenosphere, also known as the plastic mantle, you have that on page 10 in your reference table, coming up and separating. That's basically divergence. Here's another look at it, and you can see that this is found underneath the ocean. And when you look at page 5, you're going to see that most of the divergent plate boundaries are found in the ocean. That's why most of them are called mid-ocean ridges. Now, this is how it looks like, because a lot of them don't start under the water. They actually start on land and then they end up under the water. So you start with a piece of land, and as that land separates because of divergence, so if these are my 2 pieces of land, and they start to pull apart, you're going to see that there's this little, it's called a rift valley in between. So it's this lower part, and we know that water runs downhill, so water is going to run into that, and that creates these early lakes, seas, and eventually turning into oceans. Now, a great example of this is in your reference table on page 5, we have this divergent plate boundary over here on the east coast of Africa. And this divergence has created the Red Sea. We can see that there's an uncertain plate boundary as we go further south here over by, this would be Madagascar. Now this is still on land, but this is where the plates are pulling apart. And there are some really cool stories about outgassing and poisonous gases coming up and how it impacts the people that live there. So that's one of the few ones that we have on land. You can see right next to that, we have the mid-Indian Ridge, the Southwest Indian Ridge, and these are all divergent plate boundaries that are found in the oceans. So here's another look. Here's the Red Sea, there's the divergence, and you can see here's that uncertain plate boundary where it's breaking off, and you can see how it's filling up with rivers and big, huge lakes, and eventually that part of Africa is going to break off into the Indian Ocean. Now, probably the most famous divergent plate boundary is going to be the Mid-Atlantic Ridge. This is the divergent plate boundary that runs north to south through the middle of the Atlantic Ocean, right through Iceland. There are a couple of volcanic mountains that come up. Iceland is one of the most famous ones. There's also a hot spot there. If you were to go to Iceland on the land, you can actually see where the land is pulling apart. So we have these huge rifts where part of the country is moving this way and part of the country is moving that way. In this case, gives a nice visual of how that water runs downhill into these caverns. And if you were to go scuba diving, this is kind of scary for me, but you could actually scuba dive in between, like in the ocean between this divergent plate boundary. So you're literally looking at one tectonic plate on one side. This person right here is swimming through one tectonic plate on one side and another tectonic plate on the other.
Running parallel on either side of the ridge, they found strange stripes of magnetic rocks, alternating positive and negative away from the ridge's peak. Geologists know that the Earth is like a giant magnet with a north and a south pole. But the magnetic poles aren't fixed. Every 300,000 years or so, the magnetic field suddenly flips 180 degrees. When the field flips, a compass that was previously pointing north will swing to the south. As magma wells up between the tectonic plates, it pushes the seafloor up and forms the colossal mid-ocean ridge thousands of feet high. When the rock is hot and molten, its magnetic minerals line up with the north-south direction of the Earth's magnetic field. As the magma cools, the minerals are locked in position. Rocks act as a permanent record of the magnetic pole's location when the rocks were formed. As more and more magma is forced up, the old crust is pushed away from the ridge and records the reversals in the Earth's magnetic polarity.
So that video was probably the best way to explain all of this. We use the igneous bedrock because it formed from the lava that comes up out of the ridge. We use that igneous bedrock as a record of how the Earth's magnetic poles have changed over time, and they have, and they probably will again. It's something that we definitely try to figure out when it's going to happen, even though we don't have a great grasp on that yet. But by looking at the polarity from one side, this would be where the mid-ocean ridge is, from one side of that, and you can see the other side is a mirror image of it. Now, if the black indicates when the magnetic pole was to the actual north, where the north is now, we can see that the white would actually show that north was to the south, or we can just say that they flip-flop. Now, we can see that there really isn't a pattern that we can predict here. We can see that the black and the white lines are not the same width, or they're not the same spacing. But we do see, and this is important, that one side is the mirror image of the other, and that they do flip-flop occasionally. Okay. The next one is, what do we know about the age of Earth's crust? Well, if new magma is coming up at the mid-ocean ridges and turning into rock, that is where we would find the youngest rock and the hottest rock. What that means is that as we move away from the mid-ocean ridge from one side to the other, the rock gets older. So if we take right here, here's the Mid-Atlantic Ridge. As we move from the Mid-Atlantic Ridge west towards South America, we know that the age of the rock would get older, and it would also get colder. And again, that's being shown here with the red indicating the youngest and the hottest rocks. Okay, so again, to summarize here, divergent plate boundaries, they're typically found at mid-ocean ridges. They're where new crust is created. They generate shallow earthquakes because the crust is just pulling apart at the surface, and each side is a mirror image of polarity in those igneous rocks. Now, the next type of plate boundary is called a convergent plate boundary. Convergent plate boundaries, there are three types. There are ocean to ocean, where ocean crust meets ocean crust, where ocean meets continental crust, and lastly, where mountain building is occurring, and that's at continent to continental crust.
Occurs during continental drift. This example shows two large segments of continental crust colliding very slowly over millions of years. One landmass is forced underneath the other. To relieve the stress, mountain ranges are often formed in the overriding landmass, while earthquake-prone zones are formed below.
So you can see it's just two pieces of crust coming together. One piece of crust does something we call subduct.
The process known as plate tectonics occurs during continental drift.
Move to the next slide. Yeah, so the more dense one is going to subduct. Now, when ocean plates form, these create things called island arcs. The Aleutian Islands in Alaska are a really good example of this. The subduction occurs out in the ocean, so these volcanic mountains that are formed actually form out in the ocean. And again, the Aleutian Islands near Alaska are a great example of this. So is Japan, for that matter. So we know that with this, we end up with tall mountain ranges, very deep earthquakes, because one plate is subducting beneath the other. We can get violent volcanic eruptions, and because one piece of crust is being pushed into the mantle, crust is destroyed there. Now, one of the important things is when we look at the symbol for this on page 5, we can see that the overriding plate is always indicated with these boxes on that side. The subducting plate has the smooth line, and again, if it's subducting, that means it's the plate that's going to be more dense. Again, here's an example. So right here, we can see that the South American plate is the overriding plate. The Nazca plate is the oceanic plate that's more dense, is going to subduct, and we get a trench formed on the subducting plate side. And I highlighted the Aleutian Islands there for you. Okay, the last type of plate boundary we have is a transform plate boundary.
Two tectonic plates collide along the San Andreas Fault,
San
which
Andreas is
sits less than
the
40
most
miles
famous
from
one.
LA. Sitting on top of hot magma, the Pacific plate slides past the North American plate.
So you can see in this type of plate boundary, they're actually sliding past one another. So divergent, they move apart. Convergent, they move towards. Transformed, they move side by side. And again, San Andreas is the most famous one. Here's an aerial photograph of the San Andreas Fault, and you can see how one side is not lined up with the other because it's experienced that movement. Lastly, we have hotspots. Hotspots are areas of persistent volcanic activity. Some people believe where really hot, there's a hot upward motion of magma through the lithospheric plates, and as the plate moves over it, it creates these chains of volcanic islands. So on this page, we can see I'm highlighting the different hot spots. They're shown with that little star shape around the world. There are others, but those are the most important ones. All right. And in the United States, we have two main ones. That's going to be Yellowstone and the Hawaiian Islands.
Hawaii is more than 2,000 miles from the nearest collision zone. Beneath the ocean floor is a mysterious area of super hot liquid rock. Hot enough to melt a hole through the Pacific plate, punching up fresh lava. It's called a hot spot.
Oops. So the Pacific plate actually moves, we'll improvise here. So if this is the hot spot, the Pacific plate moves over it. Whoops. And each place where it moves over it, a new volcano is going to form. So the currently active volcanoes are the youngest ones. So right here. And then these are the older islands. This one used to be over here, but as the plate has moved this way, they're no longer volcanic because they no longer have that source of magma. And so you can see the islands get lower and lower as you move towards the northwest, and that's because there's no new source of rocks and they're being constantly weathered and eroded by the wind, the rain, the atmosphere, and the ocean. So they get smaller and smaller. Yellowstone is another hot spot. I'm not going to watch that video just for the sake of time. But Yellowstone, nobody really realized it was a volcano until I think it was in the 1980s when they had been studying this. And now they realize, because this is a caldera type of volcano, it's actually really low. So it has the geysers, which are pretty famous, the hot springs, but they also closely monitor it for volcanic activity. Yellowstone, of course, is also famous for its wildlife. And we always want to be careful of wildlife. Fourth block, you know who you are. And that's it. Thanks for listening. I know this was a long one. But yeah, there was a lot of material in it. So please let me know if you have any questions. Why is it still recording?